What is going to be the most important scientific discovery of the next 25 years? My answer was, you can have direct brain-to-brain communication.
Welcome to the UIUC Talkshow. Our goal with the show is to introduce you to the most interesting people with the most interesting ideas. Today we have a very special guest, Dr. Anthony Leggett. Welcome.
Thank you.
So what do you do this morning?
What did I do this morning? I went into the department and worked there for a couple of hours. And then I went out to look for a coffee, which turned out to be a rather non-trivial operation. Found a coffee in the Illini Union and worked on a slightly different topic there while I drank my coffee. And then I decided, although I normally stay at the department until lunchtime, I decided I might just as well go home. So I went home and put in a bit of work before lunch at home.
And what are you working on?
I have several different occupations right now. I'm trying to do a review of some applications to an institution in China. So I have to read a lot of the applications and try to somehow evaluate them. I'm also a member of the editorial board of Proceedings of the National Academy of Sciences. I don't know if you know that. It's one of the sort of fairly prestigious scientific journals in the US. So I have to review manuscripts for that, and I did a couple of those. And then I'm also working on an individual research topic, which is a particular metal, strontium ruthenate, which becomes superconducting at low enough temperatures. And it's a particularly interesting metal because, as you probably know, there's been a rather interesting proposal over the last 20 years or so to develop a form of computing called quantum computing. There's a particular species of quantum computing, which is called topological quantum computing, where you, in some sense, try to bury the information which you would like to keep, but you don't want nature to screw up. So you try to hide it in the many degrees of freedom of a so-called many-body system, that is a system of many atoms or whatever. So it's thought that strontium ruthenate, this particular metal, might be a good candidate to carry out this kind of operation. However, there have been various experiments over the last 20 years, and they don't seem to be mutually consistent as far as we can see, or rather, they're not mutually consistent within the existing theoretical ideas concerning this metal. And so I'm trying to sort that out in one sense or another, theoretically.
Very interesting. Good luck. I'm curious. So let's say that you went back in time and, well, maybe not went back in time, but let's say that you were an undergrad right now at this university.
Yeah.
What would you study and what problems would you work on?
Well, I think I would choose as a general field of study, I'd probably not choose physics, I think. I would more likely choose experimental neuroscience or neuropsychology. Now, which problems I would work on, I couldn't really say until I've got into it properly, but something to do with the way the brain operates, sort of things that can go wrong with the operation of the brain. I think it's both a fantastically intellectually challenging subject and also one which is pretty much direct human relevance, unlike some of the physics I tend to work on, in fact.
Why the brain? Like,
Well, it's the as far as we know, it's the most sophisticated kind of object which nature has developed. It's unclear to me whether the laws of physics and chemistry and so forth, as we know them today, are going to satisfactorily account for all the ways in which the brain works. In fact, my instinct is they probably won't. It probably will involve at some stage developing some kind of new approach to physics and chemistry, but of course we don't know until we really get into it.
That's interesting that you wouldn't study physics, for instance. I mean, even in your undergrad, you didn't study physics; you just studied the classics.
That's correct. Yes.
Right.
Yeah, my first undergraduate degree was in classics. Yes.
do you think that's better in terms of like not directly chasing what you want, but like getting the context more and then working on what you want to be working on while doing that?
Well, I would have to say that at the time when I signed up for the classics degree, I had no idea that I was going to end up in physics.
Okay.
But I also say that I have absolutely no regrets about spending that 4 years doing the classics degree, which, as you probably know, is not simply classical languages and literature, but also ancient history, ancient Indian, Greek and Roman, and philosophy. And the philosophy is pretty much what you would study if you were majoring in philosophy, say, here at the University of Illinois. Had I gone directly into physics, in some sense I would have been 4 years further on in my career. I probably might have published more papers, I got more citations and so forth. But that's of no great concern to me. I think what I got out of the classics degree was worth much more than that.
How do you think of consciousness? Like you mentioned, you would like to study the brain. And
How do I
would
think?
say, because consciousness
think
is
of
something you
consciousness?
cannot like quantize, right? Like you cannot compute. It's like currently at least.
Yeah, well, I mean, it is. It's an important question, even how you define consciousness. I think most of us have a crude idea what we mean by saying that another person is conscious or not, but that's a rather special use of the term. One can raise the question, and I've heard it raised in various meetings and so forth, about what kinds of animal might be said to possess consciousness. And the answer that I've heard, I mean, I think it's only a very preliminary one, but the answer I've heard so far is that it's most likely that consciousness would evolve in animals which are very gregarious. I mean, elephants, for example, dolphins, that sort of animals, rather than in those which are, in some sense, solitary and a bit xenophobic. That's an interesting idea, but I haven't explored it.
Yeah.
What kind of things would you've lived quite a life that many people would say in terms of accomplishments, in terms of the type of experiences you had. What do you wish you knew at our age, for instance?
What do I wish
that you knew?
Yes.
At our age.
Oh, okay. Ah, yes. Probably various things about human relations that one should recognise when one can't, as it were, take a relationship any further and terminate it appropriately. One should learn to value people whatever their relationship to you is, whether they say your boss or someone who's doing housework for you, or fellow students, fellow colleagues, or whatever. Just try to treat them in the same way. I think it took me. I mean, I hope eventually I did learn that, but it took me some time. So I think I wish I'd been a little more explicit about it at your age.
Do you mind like elaborating or like explaining more in like how, like I'm obviously, like you're obviously coming from a place of like you experienced it at some point and you would like to have done better, right? So like what happened, like can you give some context and why you would say to build better relationships, or how?
I think I'd rather not go into the details.
Right,
Actually,
right.
it's a bit too personal.
Okay.
Yeah.
Yeah, no worries. Another thing that I'm interested in is that so you worked on this problem of superfluidity,
Yes.
and it's been a while since you worked on that. But what would it look like? What kind of things could you do in a world where we're able to make these liquids in a at a great scale?
On a large scale, what sort of things could we do? Well, I think one thing one could probably do, although there are easier ways to do it, are to exploit the properties of superconductors in an everyday context. Right now, I should explain. Until until 1986, it was thought that superconductivity was a phenomenon which only occurred at very low temperatures, and therefore, to stabilize it and maintain it, you have to use liquid helium, and superfluid helium, in fact. Nowadays, we know that superconductivity actually occurs under ambient conditions, roughly atmospheric pressure and so forth. It occurs at quite high temperatures, at half of room temperature. And so there are other ways of getting it. We can, for example, we can use liquid nitrogen rather than liquid helium, and liquid nitrogen is not superfluid. So I don't actually think that there are too many things that you could do with vast amounts of superfluid helium, even if we had them, that you can't do more easily nowadays with, say, liquid nitrogen. And then, so let's talk a little about those. I don't know if you've seen demonstrations of superconducting levitation.
Right.
Yeah. Right. Mm-hmm. I've done a few myself at the farmers market, and that can actually be done on a quite sort of human scale. I mean, when I do the demonstrations at the farmers market, I'm basically dealing with little magnets which are maybe the size of a pea, something like that, and not terribly impressive. But in fact, people who want to have a sort of box office impact do occasionally levitate people on large superconducting disks. So I think almost certainly it's going to be possible to develop that further, and you can imagine a future in which, for example, transport systems use that. If we can manage to cool a large enough sample of superconductor, superconducting cable, say, we could imagine suspending a platform, a sort of little, like a little walker, but suspended in the air, and use those to propel people around. I think that could well become a reality in the next 50 years or so, perhaps. Right now, there's no objection in principle to doing it. The problem is simply that we just don't have enough of the high temperature superconductors that we need, and it's expensive and not very profitable to make them.
I've seen like people do demonstrations of like the Back to the Future skateboard,
yes,
the hoverboard, right?
yeah,
The
right,
people usually use like superconductors just to like simulate that.
Yeah, right. Yes, that's right. There's nice, nice videos you can get on the internet.
Yeah, that could be an interesting future where you can use when these materials get cheap enough and available enough that you can create this new type of transportation.
Yeah,
So it's something to look out, to be looking as the future continues.
yeah. I mean, that's just one possible application. I suspect there are going to be others, but we perhaps haven't thought of them yet.
Are such like applications being worked on campus? Do we have a big enough group or?
As far as I know, there's a lot of research on superconductivity in
Right.
general. As far as I know, we don't have any research on sort of large scale cable applications and so forth. I mean, there are many other groups which are working on that, not just here in the US, but also in China and other places.
I'm interested. We were talking about the brain, but
Yeah.
I'm interested in how your brain works.
My
So let's say when you work on your problems, when you would work on your problems, when you were in grad school, undergrad, and even after when you were your postdoctorate, when you were a professor, when you had a problem, what was the thought process like? Some people needed to understand it. Like, how do you approach problems? How do you decide what problems to work on? And what's the whole idea there?
Okay, well, first of all, how do I decide what problems to work on? I primarily look for cases where there exists some experiment, or better, a set of experiments, which we apparently don't understand within the framework of the existing theory, and then see whether I can work out how to understand them, either within the existing paradigm. Are you familiar with Thomas Kuhn's ideas of paradigms and paradigm shifts?
He wrote a famous book on science.
Right.
Please explain. Yeah.
Yes, sure. So basically, the idea is that at any given time in the history of a particular science, there will be a sort of general framework which governs the kind of questions you're allowed to ask, the kinds of answers you're allowed to give to those questions in very general terms, and the sorts of evidence that you're allowed to adduce in favour of those answers. And this collection of ideas or prescriptions or whatever you want to call it is what Thomas Kuhn calls a paradigm. And at least his original picture in his most famous book, The Structure of Scientific Revolutions, was that within any given science, you find that for a long period a particular paradigm reigns, but then there may be a so-called scientific revolution in which the paradigm will change fairly violently. And then the kinds of questions that you're allowed to ask and the evidence you're allowed to produce and so forth will have changed very considerably. So, I'm sorry, my brain is indeed wandering a little. How did we get onto this? This is because you...
We're talking about what problems to choose.
Well, yeah, thank you. Ideally, I would like to try to find a set of experiments which appear not to be explicable at all within the existing paradigm. And then obviously the hope would be that I and others would be the people who would motivate a paradigm shift, a scientific revolution. And I did at one point in my career think that I had found such a set of experiments. These were the nuclear magnetic resonance experiments on helium, superfluid helium-3 from Cornell University in 1972-3. I was actually so struck by these experiments that I thought that there really was a chance that it showed that the existing paradigm, which was essentially based, among other things, on quantum mechanics, was breaking down, and that one might have to substitute something else for it under these very extreme conditions. Well, it didn't in fact turn out that way. It turned out that it was possible to explain the experiments within the existing paradigm, but it was still somewhat non-trivial to do so, and so that was a really worthwhile, I think, research project. And it's similar, though on a perhaps slightly smaller scale, with these questions I'm thinking about nowadays in connection with strontium lithiumate. Again, we have a whole set of experiments which, within the sort of the sub paradigm which we've developed to deal with this kind of superconductor, things don't seem to be working, as it were. And so I'm trying to look for ways in which you might tweak or develop this to. I don't seriously suspect that in this case it will lead to the overthrow of anything particularly spectacular, but it may nevertheless tell us that some of the assumptions we were making, implicitly making, were not correct. So I think whichever way it comes out, it may be quite interesting.
So when you saw these experiments, the NMR, the nuclear magnetic resonance experiments, you were blown away. But did you have a feeling that something interesting was going to happen, or did we just follow your curiosity to see whatever happened? Like,
well, yes, I thought something interesting had to happen in some sense, because it was so clear that you're not going to be able to explain these within within the existing, if you like, sub-paradigm.
Right. So another thing that you mentioned is it's Thomas Kuhn, like paradigm shifts, and you said that you did it at one point. And how do you deal with the question of, here's how science works, and let's say that you come up with a new theory that basically makes everything from the past wrong or not complete. So how do you deal with, first, you have, like the world's it's compromised with humans. So you need to convince the humans, because even if you have the data, it's not enough. So you need to be able to tell a story to convince people. So do you have any thoughts on that, and how to?
Well, yeah, that relates to another project on which I've been working for a long time, which is whether quantum mechanics fails when you get up to a level sufficiently close to the everyday world. So far it hasn't. My particular specialty is trying to think of and analyse, theoretically, various types of experiment which you might do, which are pushing in this direction. Now, I've already been told by one colleague whose background is not in, as you know, I'm in condensed matter, so-called condensed matter physics, the physics of, among other things, everyday life, and not in, say, atomic or particle physics or cosmology. One colleague who came from one of these other areas once told me very firmly that he would never accept any evidence for the breakdown of quantum mechanics which came from the area of condensed matter physics. It's just too complicated. There are too many things that would go wrong. Well, maybe, but one of my pet projects has been trying to refine possible experiments in such a way that that kind of objection can't be made. So far, I'm in my mind, so if you like, slightly unfortunately, we've had no evidence that quantum mechanics is breaking down in this direction. It seems to be working fine, but who knows?
So what's your intuition on how quantum mechanics works, or will there ever be a connection with general relativity? Like Richard Feynman, for instance, it's known for saying we'll never understand quantum mechanics, and if someone says they understand it, they probably don't. So do you have a general intuition how quantum mechanics work?
Well, okay, I do have the rather strong opinion that it doesn't pay off to spend too much of your time trying to understand or interpret quantum mechanics as it's currently formulated. There are plenty of people who spend their whole working life doing just that, and I really don't think it's a worthwhile use of one's time, simply because I'm fairly convinced that in 100 or 200 or 500 years' time, people are not going to be believing that quantum mechanics is the whole truth. Now, of course, then the obvious question is, okay, what's going to replace it? But I think we're really in the position of that people might have been had they taken things seriously in 1876. Now, why do I say 1876? In 1876, mechanics, what we now call classical mechanics, but
Right.
they would just say mechanics. Mechanics was going strong. Seemed to be, together with the electrodynamics of Maxwell and so on and so forth, seemed to be explaining just about all the experiments that people could do. But in 1876, Willard Gibbs came up with what is now known as the Gibbs paradox. And this has to do with the behavior of the entropy when you mix two volumes of an identical gas. And there seemed to be some kind of contradiction there. Now, Gibbs himself seemed to regard this as just a sort of minor accounting matter. But I think that if people, with the virtue of hindsight, I think one could see, had people really taken that seriously, they would have had to come to the conclusion that mechanics, or as we would say classical mechanics, had to break down at some stage as you went from the everyday level to the level of single atoms and molecules and so forth. They would not have known when it was going to break down. They would certainly not have known how it was going to break down. But that it was going to break down, they could have known and should have known in some sense in retrospect. Of course, we now know that it did break down and it led to quantum mechanics. That would have been impossible for them to guess, but I say that something was going to go wrong. I think we're in the same position now with quantum mechanics. We don't know when it's going to fail, we don't know how it's going to fail, but that it's going to fail, I think we know. And that's why I think that one's efforts, rather than trying to find more and more sophisticated interpretations of quantum mechanics as we now know it, I prefer to spend more time trying to devise experiments which may conceivably show it's not going to work.
That's true. Like I was reading about it some time ago. Like whenever we run these experiments at the Large Hadron Collider, for example, we hope that we observe something that we weren't expecting, because that's more exciting than proving our theories, right? Because we want to be surprised. We want to experience something that we thought did not exist, and then we can focus on that and see why that happened.
Oh, yes.
Like we would want our models to fail.
Oh, yeah.
That's how we learn and like make better ones.
Yes, indeed. Yeah, that's right.
Yeah, and the goal should be, like you said, not necessarily understand everything about quantum mechanics, because, like you said, in 100 years or 50 years or however long, it will fail in some way. So therefore, our efforts, or at least part of our efforts, should be focused on designing the experiment that would prove, that would make quantum mechanics, quote unquote, fail.
Yeah, but of course, returning to your earlier question, if you have done that experiment, and it seems to you, or it seems to me that you have shown that quantum mechanics fails, how are you going to then persuade your colleagues?
Right.
I mean, it's almost certainly, it won't be a matter of a year or even a few years. It'll be a generation or a couple of generations before the community in general is likely to accept that this has happened.
What do you think about the new kind of science that was proposed by Stephen Wolfram like 20 years ago?
Well, I'm sorry, you're going to have to fill me in on that.
Right. So a new kind of science was basically like Stephen Wolfram. He wrote a book for like 10 years.
Yeah.
And he compiled all of his thoughts in a book called A New Kind of Science.
Yes.
Which is basically about how everything in this universe is computational.
Yeah.
Like every action, everything that's happening, like even relativity, quantum mechanics, like the one thing that binds all of these theories together is the fact that they're all computational.
I don't believe that. I don't believe that when I fire an electron, say, or my colleague fires an electron through a Young-Slitz experiment, I don't believe that that electron is doing a computation to decide where it has to go.
What do you think happens?
I think it just goes.
It just goes.
Yeah. I mean, this may be a prejudice, probably is on my part, but I frankly think that the idea of computation, both as a practical tool and as in the sense that Wolfram tried to develop it as a sort of conceptual primitive, I frankly think that's overvalued.
So going back to the question of like, okay, you found an experiment that would make quantum mechanics fail, and you need to convince them. So let's say that happens to you tomorrow.
Yes.
How would you go about it?
How would I go about
or like someone that you know does it. How would you? What exactly would you do?
Well, okay. I mean, I think the most obvious thing that one would do is to get the experiment repeated by various different groups. I mean, in the talk, in the sort of popular talk that I give on this, I raise this point and I say, well, you want it repeated by 6 different groups working in 6 different countries and on 6 different latitudes, funded by 6 different funding agencies and so forth. And if they all come out with the same result, then you maybe at least have a starting chance of convincing the general community, but not until then. So that's the first priority. The second, of course, the second line of defence, which most people will take, is, okay, so the experiments do seem to come out this way, and that's reliable, but your interpretation of them is somehow wonky. And in particular, in the case of trying to show that quantum mechanics is not working at the scale of everyday life, say, the obvious objection is to an experiment which tried to show that quantum mechanics is not working, is the effects of decoherence. The idea that the environment is always trying to screw up the behaviour of your quantum mechanical system, and that gets worse and worse as you go from microscopic to macroscopic. And so you've simply forgotten about some part of the environment which is giving rise to decoherence effects you hadn't worried about. And if you take those into account, quantum mechanics will continue to be okay. And that's going to be rather hard to fight, frankly. And I suspect it's going to be one of those cases where, there's really no logical argument you can give which will be 100% convincing. You be like special relativity, really. If you think about what happened there, you see, people had for a couple of hundred years really believed in certainly in the 19th century, they believed in the ether as a means of propagating electromagnetic waves and so forth. Along comes, first of all, of course, comes Michelson-Morley, and then comes Einstein, and proposes a new way of looking at it. Lots of people never accepted that. Lots of people went to their deathbeds without ever accepting it. In the end, and there were a whole string of objectors. I had actually had to review a book not so long ago, one of these rather diligent scholastic efforts by a German PhD student in the history of science about the people who opposed Einstein, not just in 1905, not even just up to 1918, but right through the 20s and 30s. There's a fairly substantial group of people who did oppose him. Well, I guess cynically you could say in the end they died off. And, the new generation was more prepared to receive Einstein's ideas, and I suspect strongly that's going to be the case with quantum mechanics if it does ever turn out, or most people think it turns out.
Is there an idea that you hold currently that you think others will say no to, but you think is right and will get maybe proven right in the future?
Yes, I think that the idea that in some way we can't even formulate right, let alone understand right now, the idea that the future can affect the present may turn out to have something in it. One way I look at this goes something like this. If you look at the really, really major revolutions in physics, I guess all of them really involve the overthrow of something which up to that point had seemed just common sense.
Right.
For example, I mean, it's common sense that the sun goes around the Earth until Copernicus told us otherwise. It's a common sense that the time at which an event occurs should not depend on the motion of the observer, Einstein. It's common sense that the universe is static, Hubble, etc., etc.
Right.
In some sense, I think the one piece of common sense that has never been seriously challenged in these past revolutions in the history of physics is the idea that the past causes the present and the present causes the future, and not vice versa. Even to really analyse what we mean by that statement is not trivial.
Right.
Let alone to ask whether it could in some sense be mistaken. But I'm inclined to think that if there is, and I think there's going to be a major revolution in physics sometime in the next 100, 200, certainly 500 years. I suspect it will have to do something in some way or another with the idea of the so-called arrow of time. Yeah.
Have there been any observations or anything that you've personally experienced which leads you to say that the future affects the present, or what made you think that this would be it?
No. Okay, I can sort of interpret that question on various levels. In the context of pure physics, no.
Right.
In the more humanistic concept,
yes.
sort of. In some sense, I don't think this is a particularly original idea, but the significance of a particular fact involving human relations, say, may in some sense not always be defined at the time. It may come to have a particular significance only in the light of what comes later. So, not a particularly novel idea, but it does lead me to think more generally that one should, in some sense, worry about whether that you can simply cut, as it were, even in physics, you can sort of cut things off at the present and forget what comes later. As you probably know, I mean, there have been there's been quite a lot of technical work in this general direction. In a sense, I'm thinking particularly of the work of Ikea Aharonov and his collaborators, where they've emphasised the fact that you can sometimes define the state of a physical system not just by how it was prepared, but by how it was post-selected, that is, by what measurements were made on it later than the time you're considering. I mean, that goes a certain way in that direction, but it doesn't really, I think, touch the sort of fundamental uncertainty that I would like to explore.
Do you have any thoughts on how time works, or what time and I mean, no one knows, obviously, but if you had to guess, what is time?
I don't really think I could even attempt an answer to that question. As you know, that's been around for 2,000 years and more. So, I mean, that's long precedes modern physics. So, I mean, time is in some sense the one of the ways in which we order our experiences. It clearly, in some ways, resembles the spatial degree of freedom, and in other ways is very different. I'm afraid really that exhausts the profound thoughts I have on the subject.
There's been some movies where, for instance, there's this movie called Tenet, and basically this movie, they figure out a way to make entropy, go back. Entropy is S,
yes.
greater or equal than zero, so it can never go back. He's always increasing. So they figure out a way to make entropy go back, and therefore they figure out a way to time travel into things. Again, not an idea that is proven by science or anything like that. But do you think something like that will ever happen some way?
I think. Well, first of all, I mean you have to be rather careful in interpreting the meaning of the second law of thermodynamics. The idea that entropy is always increasing, the arguments to that effect mostly simply rely on the fact that you set, as it were, initial conditions and not final conditions. So if you somehow find a way of, as it were, setting final conditions, then of course the reverse would be the case, that entropy would appear to decrease in time, basically by the same arguments as lead to the standard second law. Right? Now, I have played around vaguely with questions like the following. Suppose that I have a complicated system, say a cylinder full of gas or whatever, and what I do is the following. I partition the atoms into two groups. Not spatially. I just random select certain atoms to be in one group, and I'm doing this all classically because of quantum mechanics. I probably shouldn't do that.
Right.
Yeah. So I just partition them into two groups of equal size, and for one group I set initial conditions. That is, I specify their positions and velocities at the initial moment of time. And I consider a given period from t sub I to t sub f, so initial final times. The other group, I specify their positions and coordinates at the final time. And then I, as it were, let them loose and see what happens. I've sort of played around vaguely with this, but frankly not spent enough time on it to know whether there's anything interesting that will come out. I suspect the answer is yes, but as I say, it's not something that I would need a self-supported postdoc, really, I think, to work on. Someone who doesn't need to get a job at the end of it.
Are there any thought experiments that you come back to? Like if after all these years, some thought experiment that was really influential in your work?
Thought experiments.
Right.
As distinct from real ones that have been.
Right. So by thought experiment, I mean more like for Einstein, for example, right? When he was figuring out relativity, one of the thought experiments he had was if there was someone in a train and there was a lightning strike.
Yeah.
The time at which the person in the train would see the lightning strike versus the time a person outside the train would see the lightning strike, would it be the same or different?
Yes.
Right? So
yes.
Those kind of thought experiments led him to question what was understood as conventional science or physics and what made him work on relativity. So were there any thought experiments that you have had?
Well, I mean, there's the famous or infamous Schrödinger's cat thought experiment, which the idea being that, as you know, that quantum mechanics is a strictly linear theory, and if you try to tinker with that aspect of it, you really screw up the whole thing. So we better, if we're doing quantum mechanics, we better treat it as a linear theory, and then we can, of course, follow Schrödinger and imagine that you have a microscopic superposition, so a quantum superposition of two different trajectories of a single atom, right, which will, by a suitable amplification process, lead to two macroscopically different outcomes, in this case cat dead and cat alive. And if you genuinely believe that the correct description of the universe at the microscopic level is by that quantum superposition, and that should be interpreted, moreover, as saying that the atom is not doing one thing or the other, it's somehow doing both, then you're forced to the conclusion, same conclusion in the case of the cat. And yet, of course, we presume that if we were to do this experiment with real cats, and when we take the lid off the box, each particular cat is going to be dead or alive. So that thought experiment has bothered me for a long, long time, yes. And was a large part of the motivation for asking, are we sure that the formalism of quantum mechanics is going to continue to be valid as we go from the microscopic to the macroscopic level?
What would be the greatest discovery, science discovery?
Period. You mean?
Yeah, like if you could ask a genie or something, what would be the greatest science discovery that could ever that would unlock a new step in science, like a new era, a new revolution?
Oh boy. Well, okay. I was asked a rather similar question at a more limited timescale in a different context, very recently, in fact. I was asked the question, what is going to be the most important scientific discovery of the next 25 years? Okay. And I was one of several people who was asked this question, and most of them had what I thought were rather conservative answers to this question, like, say, developing machine learning to a
Right.
much greater extent or whatever. So my answer was some of the phenomena which in 2022 we call psychic and think of, as most people think of, as the product of sort of optical illusion or self-deception or whatever, or chicanery. Some of those, some at least of those phenomena, will turn out to be for real. In other words, people who have done sufficiently controlled experiments, they convince the community that at least some of these phenomena, not necessarily all of them, are for real. And what this would suggest, although it's not the only possible explanation, would be that you can have direct brain-to-brain communication. In other words, my hypothesis was that this would only work, incidentally, between very carefully selected pairs of subjects, for example, identical twins at a particular age, whatever. But what would happen, crudely speaking, is that the emitting subject would emit directly from his or her brain an electromagnetic signal, which would be strongly entangled, quantum entangled, so it wouldn't be distinguishable from noise by any normal apparatus. This would then travel to be picked up by the receiving subject, whose brain, if she is indeed an identical twin, is sufficiently closely configured with the brain of the emitting one that she could receive and register it, as it were. I think that's sort of fairly wild, but it's not totally out of the question, I think.
Is this why you were interested in neuroscience? Like,
well, I think that I tend to think, if I can just go slightly off subject, when I think about allegedly psychic phenomena,
right,
generally, generically, I will tend to ask three questions. Question number one, if this phenomena were for real, would it violate the first law of thermodynamics? And if the answer is yes, then I say forget it. Question number two, if this phenomena were to turn out to be real, would it violate the second law of thermodynamics? If the answer is no, then I say, well, go ahead and study it. If the answer is yes, I'm a little more conflicted, actually, because I'm not entirely sure that we understand all the real ramifications of the second law, or qualifications. Question number three is does the phenomenon, the alleged phenomenon, have an explanation in terms of the physics we know today? I don't care really what the answer to that is. I'll go ahead and investigate it. Because one example, which might relate to question 3, for example, is water dividing. I guess you know the general idea. Certain subjects claim that they can take a particular kind of forked stick and walk over the ground in a certain area, and that the stick will twitch when they're above water. And this is being taken sort of at least semi-seriously by some quite respectable people and organisations. I mean, for example, when the British Rail system wanted to build a line through a certain part of the North Downs in Surrey, they realised that that during World War I there had been lots and lots of bunkers, hidden subterranean bunkers built there, but they didn't know, they didn't have the records, they didn't know where these were, and they actually did employ some professional water diviners to walk over the ground and try to detect these. And of course that's not water, but it's the same general principle. So you ask yourself that, okay, that doesn't violate the first law of thermodynamics. It apparently doesn't violate the second law. On the other hand, it's not apparently explicable within any version of the physics we know today. I say by all means go ahead and investigate that. That's worth investigating, for sure.
What's the reasoning why you use the first and the second law of thermodynamics as well as the current physics? Like, what was the thought process behind asking those 3 questions?
Oh, well, okay. I mean, I would think that the first law of thermodynamics is as basic a feature of...
Very fundamental.
Yes. I mean, it goes way back to Newton, or probably beyond, in fact. If we were to throw that out, I mean, it's conceivable we might have to throw that out, but that would really involve revising just about 100% of the physics we know. So, I think that's a priori pretty improbable that we're going to have to do that. As I say, with the second law, as I say, it's less clear-cut. You have to specify rather carefully what you mean by the system, what you mean by the environment, how you're going to set the initial conditions, etc., etc. And it's only after you've done that that you can really make any firm claim, even within the context of contemporary physics.
Interesting. Thank you for explaining that. The other thing I'm interested in is and that I would like to hear your thoughts is the following. So how do you think of so Richard Hamming? It's someone that is a mathematician. He graduated from here, a PhD, and he would go on. He worked on Bell Labs.
So you say this is an actual person I'm talking about?
Yeah. So Richard Hamming. So he worked at Bell Labs and he worked with many interesting people like Bardeen and Hamming and all these people. Yeah. And something he would do is that he would sit with people and he would ask, what are the important problems in the field and what problems are you working on? Yeah. Some people would get mad at him. Some people would be like, oh, yes, it's a good question. Thank you for telling me that. And with you keep bringing out the brain. Yeah. So why aren't you working on the brain?
Why? Because there are 24 hours in a day and 7 days in a week, and during my career, of course, I was employed by physics departments, not by neurobiology departments. Now, why didn't I switch over? Because, well, partly because inertia, fair enough, but also partly because I had enough interesting things to do. And the time scale for doing those was rather shorter. I mean, I could have, in fact, at Sussex, when I was working at Sussex in the UK, I probably could have afforded to take 10 years off and train myself completely in neurobiology. A few of my colleagues actually did things which are somewhat similar. For example, one of my colleagues became a full-time expert in development studies. and there were others as well who trained as physicists and did something completely different. I did it in a sort of minor way, and simply switching from my low temperature interests into the foundations of quantum mechanics. I mean, within the physics community, as it is currently constituted, that was a sort of fairly major switch.
Right.
I didn't go further than that. I could have. Who knows what would have happened? I mean, I might have made some interesting discoveries in neurobiology. I might have just run into a brick wall. Who knows? So, I don't know. I don't believe in counterfactuals anyway. So.
I find it really encouraging that even at this age, you're still equally motivated to work on the problems, and you're still like going to your labs and like doing your research, and like what gets you motivated? What keeps you going?
Oh, just curiosity.
Curiosity.
Yeah. It's it's a nice feeling when you find that you've been able to see a problem in a way that up to now has no one has done. Yeah.
Was there anything that your parents did or something growing up that made you as curious as you are today? Was there anything interesting that you think, because generally every kid, every child,
Yes.
is curious, but for some reason once they reach 15, 20, they lose it.
They can be suppressed. Yes.
So how can we cultivate more curiosity that throughout their life they can have that childlike curiosity? Do you have any thoughts on that?
Well, you have to. First thing is you have to evolve a social or educational or whatever pattern in which it's not a disaster to be wrong. I mean, this is just, I think, a special case of a much more general situation that within the current setup, regarding academic study, education and research, in some sense you can't afford to be wrong, because then your career will not flourish. This seems to be a disaster, frankly, and I was very fortunate when I became employed by the University of Sussex, UK, that I didn't have that kind of constraint. I'd effectively, at a fairly early stage, certainly a very early physical age, in my early mid-20s, I had essentially got tenure. Didn't have to worry about my promotion. I didn't have to worry about publishing a paper every year in Science or Nature or whatever. And so it was much easier to take risks. I took a certain risk, of course, in just saying, when the experiments on helium-3 came up, I'm not going to bother about reading all the many books that have been written about nuclear magnetic resonance and so forth, because it's clear that this just doesn't behave according to those books.
Right.
I can just go on and sort of start from scratch and think about it. Because that was a risk. I could have just run into a brick wall. But if I had run into a brick wall, so what? I really find it's much worse today for people starting. I mean, you may think it's bad here in the US. I can assure you in China it's about 10 times as bad. People have to continually think about not just where they're going to get a full professorship, not where they're going to get, not how they're going to get tenure, and even how they're going to get the right next postdoc, even how they're going to get into graduate school at all. People seriously try to publish papers as undergraduates in these so-called high-impact journals, in order to get a little ahead in the competition to get into graduate school. It's terrible. Because that kind of pressure, I mean, people still, fortunately, there's still people who resist that and still manage to do good work under those circumstances.
Right.
But it's a huge drag, really. It's almost guaranteed to result in a whole lot of people simply doing the kind of problems they know they can do within 2 or 3 years. That's not what scientific research ought to be at all.
So how can we change that in places like the U.S., like where we have the chance and the possibility of changing it?
Yeah, well, that's the $64,000 question, I guess. I mean, look, in some sense, this is the result of a good thing. The good thing is that the academic world is far more open today than it was, say, 50 years ago,
Right.
to people from all over the world and people from various backgrounds and so forth. That, of course, means the degree of competition is 10 times as great. So, I mean, I think the only practical solution that I've ever been able to really suggest to someone who asks me what to do in this kind of situation is think seriously about not. I mean, assuming you're interested, you're vitally interested in physics, say, you want to do physics as part of your career, but you don't want to be under this continual pressure. So one possible partial solution, at least, is to look for a job in a liberal arts college or small community college where your main job, what you're being paid for, is teaching. This was how I interpreted my job at Sussex, basically, that I was paid to teach. If I did my teaching conscientiously throughout the week, I could go home on Friday evening and think that I'd earned my salary, honestly. And then over the weekend, possibly, I could play around with the research problems I was interested in. The employment at a small, I mean, I have no direct experience of this, I have to trust people who do. But employment at a small community or liberal arts college does to some extent fulfill that condition. And it's very interesting that when you look back on the history of the so-called quantum foundations or quantum information field, basically, in some sense, this goes back, well, certainly quantum foundations, quantum information is perhaps a rather newer thing, but the quantum foundations research goes way back to the 30s, basically. There was a long period, I would say, I don't know, probably from about 1935 through maybe 1985, something like that, in which quantum foundations simply was not a respectable subject in any major research university in North America. In Europe, to some extent, it was still respectable to do it, but not in North America. But there were people who kept the subject alive, and they were almost without exception. These were people who had deliberately made the choice to spend their careers in some kind of community college or liberal arts college. I mean, you know, I could name half a dozen names of people who did this and are now well-known names in the field. Right? Mind you, of course, there are obviously constraints on that. It's easier to do it if you're a theorist, but there are also experimentalists who manage to do that. And, it's getting less easy because even the liberal arts colleges these days tend to want you to publish in high-impact journals and so on and so forth. But at least the pressure is not the same as it is would be in a place like, well, frankly, here.
Did you enjoy working in the UK versus, like, you worked in both countries, so which?
Well, I haven't worked in the UK seriously since I came across it, which was in 1983.
Right.
Yeah.
But you spent some time in Japan as well.
So yeah. Well, yeah, I enjoyed working in all those places. Yes.
What's something that you found to be different in terms of the environment and this?
How maybe physics was done in different countries.
Yeah, well, as I say, at least when I first got employed at the University of Sussex, which was in 1967, I guess, it was possible to regard your main job as teaching and to do research in your spare time, and I really took advantage of that. So that was certainly something I enjoyed and profited from a lot. Unfortunately, even in the UK, it didn't actually last that long. Nowadays they have all sorts of research, performance assessments and so on and so forth, and so the same kind of pressure is largely there. I think it's still not as extreme as here, and certainly not as extreme as in China.
Yes, it's like this pressure, this constant like race that people, like younger people, seem in, that they need to publish papers, they need to do the right things, and there's no time or space to follow your curiosity and just follow where this thing could lead you. And this is a very modern thing that has become a reality. And like, for instance, like we're both like engineering.
Yes.
So I've realized that if you, funnily enough, like if you wanted to do engineering projects or things like that, you almost have to be a non-engineering major to have the time.
Yeah.
Because if you actually are an engineering major, you'd be just in the library doing homework and tests 24/7. So perhaps there's something to be said in that sense, like perhaps not going to the best quote unquote college in the nation because you have a lot of competition, everyone's trying to do the right thing. Perhaps it's better to not do the engineering or physics major because they're always busy or whatever. Because in a way, like what you want is leisure time to kind of let your mind wander and do that thing.
I think ideally one should, if you are at a place where the pressure is high, you should try, I know it's very difficult, but you should try to put aside some fraction of your time, say 20% or whatever, which you specifically devote to thinking about problems which not only you think you may not be able to solve, but maybe no one is going to be able to solve. And it is high risk, but I think that's really the way that really valuable research tends to get done.
We recently interviewed Bruce Byrne, and he was a mathematician who wrote basically the proofs of Ramanujan.
Oh yes, right. I know.
And after talking to him, I got really interested, and I started reading the book on Ramanujan, which is basically called the Man Who Knew Infinity.
Yes.
And in that book, I was reading that. So Ramanujan, he was very poor and everything, but because he was very talented, he's found a scholarship to go to this university.
Yes.
And in the university, he only wanted to do mathematics. He wanted nothing to do with English and the history and the literature. And well, after the first semester, after the first year, he got kicked out because he never showed up. He never did homework. He was only doing mathematics.
Yes.
And he did that once, and he came back to college a second time because someone gave him a scholarship, and the same thing happened. He only did mathematics. He refused to do everything else.
Yeah.
And what ended up happening is something that he said is that he needed this leisure time to only do mathematics and let his mind follow his curiosity.
Yeah.
So I found that story very, very much interesting because that's, after reading that, I'm more cautious, just preventing being busy all the time and just doing something and just okay, like what are the things, like you said, like spending some time, 20% of the time, or just thinking about what would the work look like if this happened, or just kind of solving these problems that perhaps cannot be solved today.
Yeah. All right. Yeah, but it's tough. It's tough to do that. Yeah.
Which is like, you need to, it's not the inertia or like how things, like the easy ways, it's kind of like forgetting your curiosity and forgetting how you are naturally like, and kind of getting lost in that way.
Yeah.
So it's a very interesting thing.
What has been the most influential era of your life?
Most influential era?
Yeah.
Well, I suppose the most, and I don't know if you call it influential, but the critical period was towards the end of my first undergraduate degree, when I decided to try to make the switch into physics. And there were many barriers, and many people who helped me overcome those barriers. And had any one of them that not worked, I would not be doing physics today.
What were some barriers?
So, well, okay. So I'm coming up to the end of a 4-year degree in the Oxford Greats, that's
Right.
critical classics. So I decide I would like to. A complicated process of thought, which is itself perhaps quite interesting. I decided that it was physics that I wanted to end up in. So I'd have to do a second undergraduate degree
Right.
in physics. Problem number one, is any university going to accept me? Well, fortunately, I was at Oxford, and there was a young tutor in theoretical physics who they just employed actually at that point, David Green. And so he was the first port of call with whom I approached to discuss this. And what he did was he sent me away for the summer. This was at the beginning of the summer vacation, and he sent me away for the vacation to read a few chapters of a really beautiful text, not text, a beautiful book. What is Mathematics by Courant and Robbins. I don't know if you know it, but it's a really beautiful book. I would strongly recommend it. And when I came back at the end of the vacation, he basically gave me a sort of little examination on the content of the chapters I'd written, and on the basis of my answers, agreed that it was not complete nonsense for me to go on and try to do a degree in physics. So that was the academic barrier overcome, and had I not been accepted elsewhere, I could have gone on at my original college, which was Balliol. Problem number two, who's going to support me?
Right.
It turned out that there was another college in Oxford, Merton College, which had a scholarship, which was usually given for postgraduate work, but in my case, they were prepared to tweak the conditions a little to make it available to me to do a second undergraduate degree. There's actually a complication there, because the original scholarship had been based on a donation by an alumnus, and the year of graduation of this alumnus was somewhere, I think, around 1850 or whatever, when political correctness was not quite what it is today. And so it was specified in the conditions for this scholarship that the holder, the recipient of the scholarship, should be an Anglo-Saxon Protestant. Well, I am half Irish, and I am certainly not a Protestant. I was brought up as a Catholic. So very fortunately, of course, we're talking now about 1959, and by that time, of course, the college had realised that this is not, at least in the modern spirit, and so they'd actually made a nice arrangement by which, if they couldn't change the conditions of it was just sort of built in concrete.
Right.
So they said, well, if if we get a candidate who we would like to accept and who satisfies these conditions, then we will accept him. But if and we'll use the money from this donation. If we get a candidate who would otherwise have been accepted but doesn't fulfil these conditions, we'll just put up our own money for it. And so that's what they did for me. Incidentally, I think the original donor had never bothered to specify that the holder should be male, and therefore I suspect there are quite a few Anglo-Saxon Protestant women who now are enjoying this. He'd probably be turning in his grave, I imagine. Anyway, so that was the academic, the financial problem overcome. The third problem, the most serious, was the military draft. Britain had the military draft during World War II and continued it for some years thereafter. And I had managed to defer being drafted when I first went up to Oxford in 1955, and that was quite a regular thing. People did defer military service to do a first degree.
Right.
But now I'm coming up to the end of this first degree, and I'm going to go to my military draft board and say, look, you guys, you've deferred me for 4 years, but I'd really rather like you to defer me for another 2 years so that I can do this second undergraduate degree. Well, it was known that 1959 was in fact the last year of the draft intake. So if I were to defer, then we don't never do it at all. So they're going to get pretty wise to that, and they were certainly going to turn me down. Right? That's where General Sergei Korolev saved me. You probably almost certainly don't know who General Sergei Korolev is. To give you a clue, he spent most of his life anonymously to avoid being assassinated by the CIA. He was the person who was in charge of the Soviet Union's space program throughout the 40s and 50s. And so it was he and his team who launched Sputnik in the fall of 1957. Okay. So you have this thing going across the sky. Everyone in the world knows that this this spaceship is first ever Earth satellite. Sorry, first ever Earth satellite has not been put up by the US or by the UK. It's been put up by the Soviet Union. All the pundits and politicians and journalists start crying out, how come that the Soviet Union has got ahead of us in this incredibly important technological area? Well, the answer came back fairly quickly. It's because we've encouraged all our best and brightest to do useless things like classics and not useful things like physics. And so this huge sort of sociological wave, if you like, which of encouragement of people to who were trained in the on the humanities side to switch to a scientific subject, and lots of scholarships and so forth became available for that. And I was able just to ride the crest of this wave. And most importantly, it meant that my tutors could go to the draft board and say, look, you guys, you want scientists, right? Well, here you've got someone who wants to become a scientist, much more useful to you. You're doing a second degree than bashing the parade ground. So that's how I got out of the military draft. And so those were really the three main obstacles. But of course, then I had to compact things. I had to complete my undergraduate physics degree in a couple of years rather than the standard 3 years without having any real high school background for it. So that was a bit of gave me a bit of mental indigestion, to put it mildly.
So how did this general save you, and why was he being persecuted?
Sorry?
So why was the general in particular like? How did someone like the general help you getting drafted? So I'm assuming there were other people too.
Because had it not been for Sputnik, I almost certainly would have had to do my military service. And it was only that wave, that sort of sociological wave of opinion that people, the brightest people ought to be encouraged to do science and not.
Right, so it was the indirect effect.
Got it, okay.
Yeah.
I thought he did something for you, directly.
Yeah.
No, he doesn't know me personally, and vice versa. But if I ever get through the pearly gates, he's one of the first people I'm going to want to thank.
Got it. It was more like they launched Sputnik, and then everyone needed to become scientists because of that.
Right, and then they started giving more importance to the people who wanted to pursue science, and
that's how they let you stay over a little.
It's pretty interesting.
Wow, I mean, it's a series of events that
fortunate events.
One of them would have been cut off and a whole different life.
Yeah, right. Any one of those things could have gone wrong, and many other minor things as well. But,
It's fascinating.
So besides that, those four events, which are probably one of the most fortunate times of your life, are there, or were there any other times where you were lucky or blessed or fortunate?
Definitely, yes. As a second fairly major point, that in the early summer of 1972, I guess I always get the years wrong, but I think it's 1972. I was working at the University of Sussex. I was working and I'd been doing some work in low temperature physics, but I had more or less, by that time, I'd got sufficiently interested in the foundations of quantum mechanics that I'd more or less made the firm decision that I was going to abandon doing just straight line low temperature physics and devote myself full time to the foundations of quantum mechanics. At that point, I went off for a week's, 10 days holiday rock climbing in Scotland. While I was, a few days before I was due to return to Sussex, I had, for some minor administrative reason that I don't recall, I had to make a phone call back to the University of Sussex. And whoever answered the phone, it would have been someone in the physics department, whoever answered the phone mentioned to me, after I got this sort of business I'd called about done, mentioned to me that Bob Richardson from Cornell was going to be visiting Sussex in a few days' time and would like to, if I were around, would like to talk to me. I had actually had some contact with Bob and some work I'd been doing on a normal state of helium-3. He'd actually done an experiment and I had done the theory, and we'd done it, as it were, in ignorance of one another's work, but then found that they did actually match up. So I had quite a sort of pleasant experience with him, and I thought I would like to talk to him, but on the other hand, I was enjoying my climbing holiday. And so when I had to make the decision, I think it was basically the toss of a coin, and probably it was raining that morning, so I decided, I probably wasn't going to get a lot more rock climbing done. Why not just go back and meet Bob? So I did, and that's when Bob told me about the NMR nuclear magnetic resonance experiments on helium-3, and got me thinking about them. And in some sense, I did get a head start on a lot of people, because this was some weeks ahead of the actual publication of the results of the experiment. And that, of course, switched me away again from the foundations of quantum mechanics into firmly back into low temperature physics. And I didn't get back into the foundations of quantum mechanics until for another 10 years or so. So that was certainly another piece of serendipity.
Wow. What advice would you have for young students like us who are motivated, who are looking to find ways to continue their curiosity and work on important problems?
Well, I mean, this is a sort of standard question that I've often got from, in press conferences and so forth, so I do have a sort of fairly standard answer, which I'll give you. Well, I think the first thing is whatever else you do follow your curiosity. If a question seems interesting to you and you don't understand what's going on, then don't worry too much if everyone else says that that's a silly question. Everyone knows how that works. I always think about Einstein in this context. For about 250 years before Einstein, everyone had known that all types of physical body, no matter whether you're talking about a stone or a feather or a bird or whatever, they will, in a vacuum they'll fall at the same rate. Einstein asked why. And I'm sure that a lot of his colleagues, I remember he was pretty junior at the time, I'm sure a lot of his colleagues say, yeah, that's a stupid question. I mean, everyone knows they just do. But of course he pursued it, and eventually out of that came the general theory of relativity. So as I say, don't be put off if people think that the question you're asking is silly. Follow it up, and until you're satisfied, don't drop it. The second thing I advise people is don't worry too much about the existing literature. It's often better not to read the 200 odd papers which have been written on the topic, but rather to see whether you can think out an approach based on the general physics that you know. That's basically what I did with the helium-3 business. I knew that there were large tomes written on the subject of nuclear magnetic resonance. I also sort of knew in my gut they couldn't be right, or at least more precisely, they couldn't apply to this experiment. And so I decided to start basically from scratch and used rather general ideas which I'd picked up about sum rules and things like that, and that did turn out to work eventually. Point 3, don't ever worry about having wasted your time. That is, if you've done let's say a theorist, okay? If you're a theorist and you've tried to work on a certain problem and it's gone nowhere, and you don't think, oh, the last 3 months were wasted. They weren't. Just write up what you've done fairly conscientiously and completely, put it away in a drawer, and I would bet that 10 or 15 years down the road it's going to come around and help you out in probably some totally different context. That's what happened to me, for example, when I was working in Japan. I did some work on so-called two-band superconductors. It was a brief period when it was thought that Niobe was a two-band superconductor. So I did a theory of some phenomenon which might occur in a two-band superconductor. And I got to the point where I actually wrote a couple of small articles on it. But then it turned out that they did another experiment, Niobe was not a two-band superconductor. So I sort of thought, well, yeah, it's a waste of time. But I did write it up. I did write the articles. I put it away. And later, that was the key, in fact, to the more microscopic work that I did in the helium-3 area. Fourthly, always try to make life as simple as possible. If you, again, this is probably more for the theory people than experimentalists, but there's a great. I found as a graduate student, and a lot of my contemporaries did, it was a huge temptation to learn up the most fancy theoretical methods and so forth, functional integrals, Green's functions, you name it. And then to just automatically apply those to any problem you facing. Well, I mean, maybe you might even get somewhere doing that, but even if you get something out doing that, don't be content with that. Try and find a much simpler, more intuitive way of looking at the problem. That'll be far more understanding than grinding through this complicated stuff. And then finally, and I think this is very important, again, I'm giving you my standard speech on this topic, basically. If you're going into academic life, either as a university teacher or as a high school teacher, then whatever else you do, take your teaching at least as seriously as you do your research. That will be not only good for you, good for your students, it'll also be good for you. I would say that at least half of the good ideas I've had throughout my career have come, at least indirectly, out of the teaching I was doing. So remember, you're not just a researcher, you're also a teacher. And take that seriously.
We have thank you for sharing that. I think that's a very like seeing that like teaching not as a burden perhaps, but as a way to get ideas and bounce off ideas of students, and especially people who have a limited understanding of the topics you may be teaching or talking about.
Yes.
And they may see it in a new way, which knowing what you know, you can take that and create something that hasn't done that didn't exist before.
Yes, right. Yes, I always made it a practice, both at Sussex and at Illinois here, to volunteer to teach courses which were not in my specialist area, because I believe that by doing so, if you have to look at the subject from scratch, well, you're in the same position as your students. You see all the difficulties they're likely to see, which you won't. But basically, if you've been doing the subject for 30 years. So. Yeah.
We have a section that we call Overrated or Underrated. So we give you a question or a topic, and you tell us whether you think it's underrated or overrated.
Okay.
Sounds good?
Sure.
Winning a Nobel Prize. A lot of people say that winning a Nobel Prize could become problematic because you become very famous, you get invited to a lot of committees, and you also have the add-on pressure that you need to work on these big problems. And usually, important problems, important ideas start with little acorn.
Yeah.
So, winning a Nobel Prize, underrated or overrated?
Probably overrated, I would say. But you have to remember, people do react to it in very, very different ways. I mean, some people, one of the things that happens, as you essentially said, is that you get all sorts of invitations to go to meetings in nice places where you might meet people in quite different walks of life. You might meet journalists, politicians, or whatever, whom you would not have done if you had not got the Nobel Prize. Some people take that up and accept all these invitations. Other people, at the other extreme, there are people I know who've got the Nobel Prize who've simply not allowed it to affect their lives at all. They've just gone on working in exactly the same way as they've been doing for the last 30 years or so. I'm sort of somewhere in between, in the sense that I used to get a lot of invitations to give purely physics talks or public outreach talks. I used to get a lot of those even before I got the prize. They've sort of doubled, I suppose, after I've got it, and I do tend to accept those because I believe it is important to propagate scientific ideas to the general public. But I don't usually accept the invitations on Capri to meet with the politicians and journalists and so forth.
Right, and the other argument is also that Nobel Prize, like winning a Nobel Prize, signals the end of your project, right? Because it means that you accomplished what you wanted to, like you've proven it, and the world acknowledges you for it. So it's kind of like the end of the project, which may or may not be true in some context, but that's another argument which also people make. Like,
yeah, well, again, it depends a lot on the individual.
Right.
I mean, I think, to be honest, I don't think I've done a huge amount of. I mean, if I had to name the things I'm most proud of in my scientific career, most of them were before 2003, which is the year that I got the prize.
Right.
Not after, but I don't think that has much to do with the prize. It just has to do with the fact that I'm getting older. Had I not got the prize, I'd probably been the same.
The next one, string theory, underrated or overrated?
Well, okay, complete. This is a judgment of a complete ignoramus, really. I mean, I have not seriously studied that area at all, but from complete ignorance, overrated. So.
There's also the competing theory of, like the quantum theory of gravity.
Yeah.
Like gravity. So, what do you think of that theory as opposed to string theory? Because those are like on the other. They like try to like say, oh no, I'm the fundamental theory. No, this is the fundamental. So.
I mean, quite frankly, I've never been able to get all that interested in that controversy. And I think the reason I've never been, I mean, obviously in some senses intellectually very, very fundamental, very fascinating, but there's very little you can actually do within the scope of one's ordinary life to which will make any impact on that. That's why I like condensed matter physics, because if you have a new idea, the odds are you can ask your experimental colleagues to actually test it. And I've done that several times in my career, and that's very satisfying. I find, and I wouldn't have got the same satisfaction out of particle physics.
That's true.
The next one, the University of Illinois, when you got here, I think 1983 or around the area.
Yes.
That age. And after many years, many decades, I'm sure you got many invitations to go somewhere else and offers and things like that, but you still decided to stay.
Yeah.
University of Illinois, overrated or underrated?
Underrated, I'd say probably. No, I think we have got a very good, we've got a spectacular department here, and that's been maintained for many years. I mean, obviously it's people like John Bodine and David Pines and so forth who really kicked it all off, but I think their tradition has been maintained. And one of the one of the things, of course, we do always pride ourselves on rather strongly here is the close connection between theory and experiment. And that's something I've always tried to maintain as best I can. I had a very, very nice, very satisfying instance of this in the early 90s when I managed to collaborate with Darrell van Harlingen, as an experimentalist, to do an experiment on superconductors, which was quite impactful, I think. And moreover, I think we have a very congenial. Well, I don't know about whether the university as a whole is congenial. My wife, at one point or another, had some business in other departments. I won't say which ones, but I think her experience might have been a bit different. But I think certainly in the physics department, we're very, very congenial and supportive, mutually supportive atmosphere. Been a very, very, very comfortable environment in which to work.
Last one. The title of a knighthood, getting knighthood. Underrated or overrated?
Overrated.
Overrated.
Yeah.
How was that experience for you?
Well, okay. I mean, it's one of the many things many traditions which the UK has kept up, which from a logical point of view, really, it doesn't fit in the contemporary scene.
Right.
People get people's response to the offer of a knighthood is obviously rather different. Some decline it on principle because they don't believe in honours. I was rather tempted to decline it on the grounds that I believe, if you like, in honours, but I think they should go to people who don't have other ways of being honoured, which I certainly do. So, but my family wanted me to get the knighthood, so I didn't. So I mean, the ceremony is quite nice, and all the traditional trappings and so on and so forth. And in my case, I did actually get to meet the Queen. I mean, that's not automatic, because nowadays the odds are you're going to be knighted by a minor member of the royal family. But I was just lucky. I happened to be on the day when the Queen was doing it, so I did exchange a few words with her.
What did you tell her, or what did she tell you?
Well, the first thing, her first words to me arose out of the fact that she had to pin some kind of medal on the lapel of my jacket. It all been sort of fitted out by the assistants beforehand, so that it should have been easy to do. But for some reason, it wasn't. She was fumbling with it, and her first words to me was, "I always have trouble with these things, you know." But then we just exchanged a few words. So I suspect. I'm very sure she has some kind of prompt. Prompt. But she asked me about my Nobel Prize, etc., and we just had a couple of sentences, basically. She had to do about 100 people that day.
Oh, wow. Okay, so when it happens on a big scale.
Most of those were not actually knighthoods; they were lesser honours. But there were five of us. Well, technically speaking, there were 4 knights and 1 dame in my group. And I remember some of them. There was the chief rabbi of the UK. He got a knighthood. There was a police chief, I think. There was the head, and there was a woman who was the head of a big London hospital, and she was the one who got the damehood, as it were. Yeah.
Very interesting, and something you would have never been able to predict.
No.
Starting out when you were studying in London, trying to transfer to physics, and avoiding being drafted.
Right.
Was there anything else that we didn't get to talk about that you would like to mention or say?
Well, one part of my experience, which I suspect is not that common among people who've grown up in the developed world, is that I did spend a certain amount of time in the third world, a certain amount of professional time, as it were, and in particular in Ghana, in West Africa. And So that's somewhat unusual, and it only happened because we, at Sussex, we had a sort of exchange arrangement with a university in Ghana. But I think it was for me, an interesting part of my experience.
How do you think that affected your worldview and perspective?
Well, I think it certainly affected my view of how the developed world, meaning in my case the UK, should interact with their former colonies like Ghana. I mean, I think the educational system in Ghana was was more or less a carbon copy of the British version. And so when I was there, I obviously had to follow that, and I had to teach a standard syllabus in quantum mechanics, solid state physics, or whatever. That didn't really seem what was needed there. In a country like Ghana, you have to remember Ghana is it's sort of, I don't know what you call it, it's among what people normally think of as third world countries. It's sort of intermediate rank, really. It's not among the very poorest, but also not among but it's not like, say, India or Brazil, nothing like that. So that, from the point of view of technological development, they're sort of middle rank there. And what very seriously needed is many more people than currently are there with basic technical skills. Really pretty basic. I mean, motor mechanics and things like that. When they held while I was there, they held a celebration for the 25th anniversary of the University of Science and Technology in Kumasi, which is where I was based. And so they decided, among other things, that they wanted to erect a flag, the university flag. If you were doing this in, say, the UK or the US, I think the odds are that you would get you'd go out to a local firm to get the flag sewn, and you would go out to some local engineering firm to get the flagpole erected, and so on and so forth. That doesn't exist in Ghana. So it was the flag had to be sewn by the Department of Fine Arts of the university. The flagpole had to be erected by the engineering department. And there are lots of things like that. The university has to play a role that it doesn't have to play in technologically developed countries. And so I think you really need a lot more people at a sort of very basic technological level, and the university has to be prepared to engage in training those people far more than it was doing, at least in my experience when I was there. The courses, I think I was not the only one who came to this conclusion. There were other expatriates who've been there much longer than I had who came to the same idea, and some of my Ghanaian colleagues also. So you need much more sort of hands-on courses. Most of these kids, I actually volunteered. My second time out in Ghana, I volunteered to supervise the first year labs. And I came to realise that these kids came from the villages around Kumasi, most of them not even from the city. What had they seen, as it were, in the way of technology during their high school training, say? Basically, the most sophisticated, most technologically sophisticated item of traditional Ghanaian technology is the hand loom. And by Northeast Asian standards, the Ghanaian hand looms are pretty primitive, frankly. They go from there pretty much direct to the motor car. So the motor car to them is liable to be just a black box. And to many of my students it was. They didn't have the experience of just playing around with all sorts of, not even a radio, but things like, I don't know, can openers. Well, can openers probably did have, but slightly more sophisticated kitchen tools and so forth. So, some of them, nevertheless, were very smart and managed to pick it up very quickly, but others really didn't. And you have to give them that kind of hands-on experience of playing around with mechanical things. And and some of my colleagues were actually quite involved in trying to develop an alternative syllabus along those lines. And I think that was very
Interesting.
I mean, there's probably a much deeper political, sociological lessons I could have learned, but I'm afraid I didn't, because I was mostly focused on what I was doing.
In teaching. Yeah, it's in a way like the universities would play a larger role that perhaps in a country like the US would be specialized to perhaps.
Yeah, absolutely. Yes, that's exactly right.
Yeah.
Yes, that's right. Yes.
Interesting. I wonder if that's still true and how you could do something about that.
Yeah.
Yeah. Interesting. Then before we end, we have 2 audience members here. So I wonder if you guys have any questions or anything before we wrap it up.
The example that you used for the African children and their technological experiences, do you think it's important to do public outreach for more theoretical topics, like your work in physics, for the general community?
Yes, I think it's important because it gets across to the general public that scientists are not some sort of very special elite who are doing things that no one else can understand. That many of these ideas are things which, given a certain amount of effort, and you really can understand. Unfortunately, I suspect that you're really mostly preaching to the choir. That is, that the people who tend to come to these public lectures and so forth are not the ones who really need the message. You want to get it across to the people who are really just sceptical of science as a whole, and they're not going to come to these things. So I don't know what you do about that.
I see. Thank you.
How would you recommend lay people, people not in traditional academia, studying science, either as a hobby or wanting to maybe go into it professionally from an unorthodox angle?
Well, I think the obvious way to go about at least starting that kind of process is by reading a lot of articles from, say, Scientific American or Physics, or at least somewhat higher level Physics Today, and so on and so forth. That's basically the way I approached it when I had volunteered, to do a course on general relativity and cosmology. I knew nothing about the subject when I was starting out, so I basically I quite literally started off with Scientific American and worked upwards from there, and it sort of works. But I mean, there really are quite a lot of rather good discussions of these fairly advanced topics in that kind of journal, and one should take advantage of that, I think.
Within that context, would you say textbooks and standard curriculum underrated or overrated? Or maybe accurately rated?
Probably overrated, I think. Well, I don't know. It depends what you're talking about, really. I mean, if the subject is well established, like, say, classical mechanics, and there are very good texts. I would particularly cite Goldstein's book on classical mechanics. There's certain things which are well established, which no one seriously worries about, and so it is worth spending a certain amount of time working through those texts, I think. When you're talking about a more rapidly evolving subject, then perhaps it's better to spend your time looking at the sort of Physics Today, Scientific American type of literature.
As lay people, I think, or as a lay person, I often find it difficult to figure out which papers or articles are the relevant, accurate, important ones to read. The advice I've heard is look at the method and be really rigorous in seeing if this is actually a real replicable experiment. Besides that, what would you say is a good way to tell which articles are maybe fact from fiction and also important or not important?
Oh boy. Well, I would say if you enjoy it and feel that you you can understand it, and moreover understand it at a sort of reasonable rate of reading, as it were, then it's probably something you should go ahead with. If you find that you're just getting too many symbols that you don't, either the author only defined 60 pages ago and so forth, it's probably not the thing to read.
Awesome. Thank you so much for coming and talking to us.
Well,
We had a lovely time. So
Me
thank
too.
you so much.
Thank you.
Thank you.
And thank you for watching. I hope you had a fun time learning about thermodynamics, particle physics, consciousness, and all the other topics that we talked about during this conversation. One of the most inspiring things about this conversation for me personally was the fact that even after all these years and working on so many important problems, Sir Leggett is still equally committed to solving the problems that he wants to solve and is still continuing the research and still finding new problems to work on. And I would say the result and the consequence of that is that he has just been following his curiosity and in the way, I think, inspiring many others to do the same. Having such conversations inspires people like us, especially, to realize the importance of finding important problems and trying to work on them. And like you mentioned, trying to live a simple life. That's something that we forget in the way. And we always try to find the most complicated or the most important problem that we think would be the work on. But sometimes the answer is simple. And just trying to find a way to reach to the bottom of that problem and just chasing that curiosity is the most simple way forward. So live a simple life, follow your curiosities, and we'll see you next time. Thank you.
Thank you.